In the last episode, we saw why Kubernetes puts one common API boundary between its components. But that immediately creates a concern. If every read, write, and watch goes through one place, does that place become a bottleneck or a single point of failure? First, imagine the simplest but most fragile setup. There is only one API server process behind the cluster's API address. Every user request, every controller update, every scheduling decision, and every kubelet report must pass through that one process. So if it becomes slow or goes down, the entire control plane is affected. The API server does much more than handle an occasional command. Some requests create or update Kubernetes objects. Some requests simply read the current state. Others keep a connection open and wait for new changes. As the cluster adds more nodes, workloads, and controllers, all of this traffic increases. Now imagine that this one API server stops working. The applications that are already running on the worker nodes usually keep running. But Kubernetes can no longer coordinate new changes. New requests fail, controllers cannot receive updates, and new pods cannot be assigned to worker nodes. Kubernetes should give clients one stable API address to connect to. But that does not mean only one API server has to run behind it. The real question is whether that single address depends on just one server. In a highly available control plane, clients connect to one stable endpoint. Behind that endpoint, a load balancer checks which API servers are healthy and sends each new connection or request to one of the available replicas. This changes the capacity problem. When one API server is no longer enough, Kubernetes does not need a completely different architecture. Another compatible replica can be added behind the same endpoint, and the load balancer can begin sending it traffic. Multiple replicas solve only half the problem. They cannot each keep a private copy of cluster reality. If one API server believes there are 5 pods while another believes there are 3, the stable endpoint would return a different answer depending on which replica received the request. The API servers, therefore, do not own separate cluster truths. They all read and write the same durable Kubernetes object state stored in ECT. The API servers are interchangeable front ends to that shared state. Consider one write operation. A client asks to change a deployment from 3 replicas to 5. The load balancer sends that request to API server 2. That replica authenticates, validates, and authorizes the request, then persists the accepted object change in ECT. A moment later, another client may be sent to API server 1. That replica can return the updated deployment because it uses the same shared state. Clients are not tied to the replica that handled the previous request. For high availability, ECT is also normally a cluster rather than one database process. Its members use consensus to agree on the ordered sequence of durable writes. A majority must agree, so the control plane does not accept several conflicting versions of the same Kubernetes object. Now return to the original failure. If API server 2 disappears, the shared state is not lost. The load balancer marks that replica unhealthy and stops sending it new traffic. Requests continue through the remaining replicas. However, there is one practical detail. A watch is a long-lived connection to a particular API server. If that replica fails, the connection breaks. The client reconnects through the stable endpoint and continues through another healthy replica from the last resource version it remembers. This is why API servers are often described as stateless. That does not mean they remember absolutely nothing. They maintain connections and use in-memory caches. It means the durable cluster truth is not trapped inside one API server process, so a failed replica can be replaced. The full design now fits together. Clients see one stable API endpoint. A load balancer spreads traffic across healthy API server replicas. Those replicas enforce the same API contract and use the same durable ECT state. Capacity can grow, and one replica can fail without erasing cluster reality. That is the illusion of a single API server. Kubernetes gives clients the simplicity of one logical endpoint without requiring one fragile process to carry the entire control plane. The interface appears singular, while the implementation is replicated. But the architecture now raises the next question. If several API servers share the same ECT cluster, do thousands of reads and long-running watches all have to reach ECT directly? How does Kubernetes protect its state store from being overwhelmed?